One way to figure out whether anyone else is using an object at a time that you might free it is to just keep a count attached to the object. That is, when we allocate an object with malloc, in addition to a tag and the rest of the data that goes in the object, we also leave a little room to keep a number that we start out at 0. And then whenever you want to hold on to an object because you're referencing it from a register or from another object, that is a place where you increment the count. You keep track of that particular reference. And then whenever you stop using an object because you replace a pointer that's in a register or you change something in a record, then we decrement the count. And when that count goes to 0, then you know no one else is using it, and so it can be freed. And when you free it, then anything that object that you freed references, that goes away too. So it can kind of cascade. Let me show you this in a picture. So in this picture, the top boxes here represent registers, and we're going to draw abstract pictures. So maybe this is kreg and this is vreg, or it doesn't matter. We just have two registers. This blue box is our memory, where we allocate into, and each of the squares inside of that are allocated objects. And each of these objects, I've written a reference count on them. So the reference count corresponds to how many orange arrows come into that box, because an orange arrow means a register referencing this object, or this object referencing this other object, or so on. So this object has a 1 on it because there's 1 arrow coming in. This object also has 1 on it because there's 1 arrow coming in from the register. But this object down here has 2 because there's a reference coming in from above and also from below. Now let's suppose I change this reference here that goes from this object to this other object, and we move that reference, we put this object in that one instead of this. Right? So we're going to move this orange arrow. As I do that, then I decrement the number from 1 to 0 because this object is no longer referring to it. Meanwhile, this object is now referring to that object, so its count goes up to 3. There are 1, 2, 3 arrows coming into this object now. Now because I changed this number to 0, that means we don't need that object anymore, and we can deallocate it. And when we deallocate that object, the orange arrow that was going from that object to this one goes away, and so this number goes back down to 2. So what you see from this example is when you change registers or objects to point to different registers and objects, then you have to update the reference counter, and that may involve changing some other reference counts as you go. It doesn't matter whether it's a reference from an object to another object. It's the same thing with registers. If this register is referring to this object, and then we make it not for a while, maybe it's going to point to some other object, the fact that we drop this reference means that we drop this reference count down to 0. Since that goes down to 0, the object goes away, which means its reference to this object goes away, and so this object goes down to 0, which means that object goes away as well. So by maintaining these reference counts and deleting things when they go down to 0, we can release objects when they are no longer used. If you look at it in code, it would be something like this. We are going to continue using pattern matching and record allocation here, but you know that there's a malloc inside of there. We're going to focus instead on the reference counting, the drop operations that decrement the reference count on a particular object, and refadd that increments that reference count. So here, because we are interpreting a funny expression and we're about to return a new value by allocating closure, we're no longer referring to whatever is currently in vreg. So that's why there's a ref drop here. Now when we allocate a closure, we assume that it also increases the reference count on invreg. The body expression here is code, it's in ROM, we don't need to deal with that. But the environment, we are now referring to it to a new extra time in this closure, so we assume that close is incrementing the reference count there. Meanwhile, we just allocated this closure record and its reference count starts at 0, so we need to increment it because we want to hold on to it inside of vreg. That's a relatively easy case. If we look at doapp here, we are going to replace the expression register. Again, the code is static, so we don't have to worry about it. But the next thing is that we're going to replace the environment with a one extended from the closures environment. So we stop referring to the old environment object with a reference decrement here. Then we create the new environment record indirectly. That's going to keep it's going to internally bump the reference count on the value and the closures environment that this new environment is referring to. And since we put that into mvreg, then we increment the reference count there. We're also going to replace the continuation to refer to this old one. But we do things in a careful order here. First, we increment our reference count on the new continuation, and then we drop it on the old continuation. And that's because the old one is referring to the new one. We need to not have this one go to 0 and lose our k before we keep it in the kreg here. So that illustrates how not only do you have to be careful to put all the right reference add and ref drops in the right place here, you also have to be very careful about the order to make sure that you don't throw away something that in fact you are still using. There's a deeper problem with reference counting though, and that is that in a setting where you can have cycles among the objects, then reference counting doesn't do the job. It turns out we can't have cycles in our current interpreter because we have no state and no recursive function. But if you did, and if you could create something like this reference cycle here, or let's just make another cycle over here. So I've got a register referring to this first object that refers to another object that refers back to that first object. So a 2 here because we have 2 incoming arrows. Let's suppose that, again, we change this register to not refer to that object. So the reference count goes to 1 here. It doesn't go to 0, so there's nothing left to do. But notice how these two objects are just an island here. Nobody else is using them. That means no one else will ever use them, and really they're taking up memory without contributing to the computation anymore. Again, it's a general problem with reference counting and cycles. So if you have cycles in your data, then you need a different strategy for managing memory and deallocating things that aren't used anymore.